Hi, welcome to the continuing discussion about implementing adders and how we can speed the performance of the adder. And just to recap here, what we did previously, we looked at the PG logic as one method to improve the speed of the adder. We looked at the adder, which is a carry ripple, carry ripple adder using PG logic, and we have seen that the delay function, okay, it is of order n, right? Uh, we don't like that. This is not good, okay, not efficient, okay. So we need to change that. There are two other techniques that we're going to explore in this lecture, which is the carry look ahead adder and the tree adders, okay, where the carry look ahead can bring down the complexity of the delay to a square root of n. The tree brings down the delay to a log of 2. Well, this 2 can change, but let's say log of n to the base r, where r could be 2 or 4 typically, okay. I'm not sure if we have 8, but so that's the logarithmic complexity, which is fast. Okay, now so let's take a look at the carry look ahead adder and see how it does that. Okay, so we go back to the lecture here, and basically here we are adding 16 bit. So A is from A1 all the way to A16, and we are added to bit 60 bit B from B1 all the way to bit B16. The concept here is the following. So n here equals 16. So what we try to do here is that we try to find a small numbers where small n and small k, if we multiply them, we will get n. So in this example, we chose small n to be 4 multiplied by small k, which we chose to be 4, and that gives me 16. Okay. Now notice that n times k equals the uppercase n, and the uppercase n is the data width. And what we do then is the following. For this n, right? For the small case n, or what we do, we have these in bit adder, in bit adder, in bit adder, in bit adder, and in bit adder. How many of those? Well, notice that I need 4 bit, 4 bit, 4 bit. How many of those I need? I need k of those, the small k. So I need k in bit adders. Now, what I do then is that I connect them, okay? So I connect them such that every one of them receive a carry, okay? Every one of them receive a carry, right? And it assumes that as if it is a 4-bit adder with its own carry. Now, the trick is the following. The trick is that I need to provide to all of these this carry, so all of them can fire as quickly as possible. So the trick is to find, well, carry in, there is no difficulty to find C4 and C8 and C12 as fast as possible. As fast as possible. Now, to do that, what we do, we use a group propagate logic. So this is here the square. This square here is group propagate. We feed it off B1, bits of A's and B's from position 1 to all the way to 4. And we generate, notice, a group generate and a group propagate for the bits from 4 to 1. Then what I do, I use this to create the C4. Notice the C4 equals what? Well, the C4 equals either G4 from bit 1 to 4 to 1, or 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 uh, 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 propagate the Cn. Okay, this is from 4 to 1. Okay, 4 to 1. Okay, and this is exactly this expression here. If I do that, I generate the C4. Okay, and now notice that the C4 is fed to this 4-bit adder. Now here what I do, I use the group propagate, but now the group changes from state 4 to 1. It is from 8 to 5, bit 8 to 5. So now notice the C8 here, the C8 here is generated. The C8 equals the generation, the group generate from 8 to 5, or I propagate C4, but provided I have propagation from bit 8 to 5. And this is what we do in this logic here. Okay, so I generate C8, and notice I feed it to this 4 bits here, and this will generate for me the sum from 12 to 2. So notice that Cn here, the 4-bit generate the sum from 4 to 1. The C4 here is fed to this adder, and we generate the sum from 8 to 5. And C8 is fed here, and we generate the sum from 12 to 9. Then we take this C8 as well, and we AND it with the result of this group propagate for the bits from 12 to 9. Similar scheme. So C12 here equals what? C12 equals what? I either generate the group generate from 12 to 9, or I have C8 and I was able to propagate it from bit to 12 to 9. Okay, and this is what we are doing in this logic, and I generate C12. Similarly, I can generate C16, which is the C out of this adder, and the C12 goes to the 4-bit adder to generate what? To generate the 16 to 3 sum. Notice for these adders here, they once they get their carries, they are independent of the rest of the adder. Okay, they add the 4 bits that are designated for. So here we add from bit 1 to 4. Here we add bits from 5 to 8. Here we add 12 to 9. Here 16 to 13. So the trick is to provide these carries as quickly as possible. Okay. Now, so what is the delay for this adder? Well, first of all, notice that this we have to generate these PG terms, okay, and we have this XOR for the sum, and we have this to go through this delay of PGN n, which is this one here, okay, and then I have these and or, okay, these and or gate, they exists here, number 1, number 2, number 3, and they do exist in these adders here. Okay, so how many of those I have? I have n minus 1 in the little adders, and k minus 1 between those adders. Okay, so now notice that this delay here, n minus 1 plus k minus 1 the delay of and or gate. Now, what do you notice about this expression right here? Okay, well, what I notice about this expression is that the big N is not there. Okay, let's use a different color of pen. So the big N is not there. I don't see the big N here. I don't see the big N in this expression. What do I see? I see the small n and the lower n. The PG, and those are almost, we can consider them constants, if you will. Now the small n and the k are what? to the first degree order, we can say that, okay, so we say that n equals small n times small k, right? And the small n and the small k are shown in the expression here. So we can say to the first order degree, we always try to have n as much as possible equals to k, to the first degree order. Which means to the first degree order, this equals n squared, which means that n equals to the first degree square root of n, which means that this expression here, the complexity of it is of order of n, which is equal of order square root of n, because n is almost square root of it. And I notice that here I have the uppercase n is 16-bit, the smaller n and the smaller k are 4 bits. Okay, so we can see now we have dropped the complexity from n all the way to square root of n with use of carry look ahead adder. Okay. And now somebody might say, what's inside this PG logic here? And this is very simple. We have studied the PG logic here. They are very similar to the carry expressions. Okay, so the P is the ending of all the P's, and the generation is similar to the carry for that we have studied earlier, but without using CN. Okay, all right. So this is the logic. Now, the tree adders, on the other hand, they will drop the delay further with log of n, and we can see that this is needed for the first stage to delay through the delay of a tree adder. We need the first stage. We need the addition. So this is XOR the last stage, and the intermediate stage we need to go through log of n delay of these gates, which is and or gates. Okay, and so notice this is log of n is much better than square root of n, and definitely much better than n. So that's what you get from tree adders, and they are supposed to be the fastest adders that we have. And there are many examples of those adders that exist in your textbooks and literature. And I'm going to leave this for your own reading to explore, because the material for such is for higher level classes. Okay, so with that, we conclude our discussion of adders, and thank you very much.